In this lesson, you will get to practice pH and pOH calculation for strong acids and strong base. Please read OER textbook chapter 14.6 for more detail of this chapter section. Again, here are the list of 6 strong acids and 6 strong base that you must know. These are strong acids and strong base because when they dissolve in water, they completely ionize into ions. For example, when the strong acid hydrobromic acid dissolve in water, it will completely dissociate into hydronium ions and also bromine ions. That means if you start with 100 molecules of hydrobromic acid, the amount of hydronium ions that will be produced will be the same because the stoichiometric ratio between hydrobromic acid and hydronium ions is 1:1 ratio. You can apply the same idea to molarity as well. Molarity is unit of mole in a liter. So that means if this solution is in the same volume or in 1 liter, we can say that every 2 mole of hydrobromic acid in 1 liter would also produce 2 mole of hydronium ions in 1 liter as well, or 2 molar. The same concept will also apply with the strong base, such as sodium hydroxide. 100 molecules of sodium hydroxide would also produce 100 molecules of hydroxide ions. Same thing for if you have 2 molarity of sodium hydroxide, it will also produce 2 molar concentration of hydroxide ions. Again, these concepts apply to only strong acid and strong base because as we know that strong acid and strong base are completely ionized. That means whatever that you start with, it will always convert to the product completely, which means at the end of the reaction, there will be no molecule of the reactant left. There will be only the molecule of the product. Next, I would like you to pause the video for a few minutes here and complete the base ionization of calcium hydroxide and predict how much product will be produced. When calcium hydroxide dissolves in water, it will produce calcium ions and 2 hydroxide ions. Per equation, you can see that every 1 mole of calcium hydroxide would produce 2 mole of hydroxide ions. So that means if you have 100 molecules of calcium hydroxide, the amount of hydroxide ions would produce would be 200 molecules. And if you have 2 molar calcium hydroxide, the amount of hydroxide ion that will be produced would be 4 molar. Why is it important to understand the dissociation of strong acid and strong base? Well, because the pH and pOH calculation depend on the amount available of the hydronium ions and hydroxide ions in the solution. That means if you know how much proton available or hydroxide available, you can use those concentration and plug into the negative log to get pH and pOH. Here is the summary of pH and pOH equation that we learned from the previous chapter section. We know that if you take negative log of something, that's going to become p scale of that thing. For example, if you take negative log of proton, it's going to become pH. If you take negative log of the OH, it's going to equal to pOH. And in order to do the anti-log to get just the concentration, you would use 10 to negative pH to get the concentration of proton. Same as for the concentration of hydroxide ion as well. If you do 10 to negative pOH, you are going to get the concentration of hydroxide ions. And recall from autoionization of water, the Kw of autoionization of water is equal to 10 to negative 14. Which is equal to the concentration of proton times the concentration of hydroxide ions. If you take negative log on both sides, you are going to get the pH and pOH scale that when you add them up together, it equal to 14. Let's use this equation right here to complete example 1 and 2, 3, and 4. Please pause the video now and complete them. Once you finish, you can resume the video again. Example 1 asks us to calculate pH of strong acid HCl. Again, hydrochloric acid is a strong acid. That means the concentration of the strong acid would be the same concentration as proton or hydronium ions. Again, because it's dissociate 100%, so that means the ions that produce would be 100% of what originally is. Therefore, the pH of 0.0031 molar hydrochloric acid would equal to negative log of 0.0031, which is equal to 2.51. Again, two significant figures from the concentration would then become two decimal places in the pH value. Next, let's take a look at 5.8 micromolar hydrochloric acid. Again, this is the prefix that comes before base unit. Micro means 10 to negative 6, so that means the concentration of this is equal to 5.8 times 10 to negative 6 molar. To find the pH of this concentration of hydrochloric acid, again, you are going to use negative log of the concentration of the proton, which is the same as the concentration of the strong acid, because strong acid dissociate 100%. When you take a negative log of 5.8 times 10 to negative 6, you will get 5.24 as the pH for this solution. Again, two significant figures from the concentration will become two decimal places in pH value. Please note that the solution that we are looking at right now is an acidic solution. That means the pH value should come out to be less than 7, which makes sense. Next, when you take negative log of 2.2 molar of hydrochloric acid, you are going to get negative 0.34. Can a pH be a negative value? The answer is yes, it can. If the concentration of strong acid is very high, you are going to end up with a very, very small value of the pH, indicating that this solution is very acidic. And again, because pH and pOH are constrained by the 14, so that means if the pH of 2.2 molar hydrochloric acid is negative 0.34, that means the pOH for this solution would equal to 14.34, because as long as these two add up together to give the 14, these two values are correct. Next table asks us to fill out the pOH value for these two base solution. One is potassium hydroxide, the other is calcium hydroxide. Again, these two base solutions are strong base. They both are one of the 6 strong bases, so that means in this case, in order to get pOH, you are going to take negative log of the concentration of hydroxide ions. Because they are strong base, so that means the concentration of hydroxide ion would be the same as the concentration of the base. So if you take a negative log of the concentration of the base, which is 0.074, you are going to get pOH of 1.13. Again, this is the base solution, so the pOH value have to be less than 7. And if you are going to calculate pH for this solution, then the pH value for the base will have to be greater than 7. For strong base calcium hydroxide, you can see that a strong base calcium hydroxide, when it's dissociated in water, is going to give 2 mole of hydroxide ions. So that means the concentration of hydroxide ions for this solution would be 2 times of the concentration of the calcium ion, which is 0.055. So that means the concentration of hydroxide ions would come out equal to 0.11 molar. To take negative log of this 0.11 molar, you are going to get 0.96. Again, this is the pOH of the base, so that's why the pOH value will come out less than 7. And also because the concentration of hydroxide ions in calcium hydroxide is a lot greater than in potassium hydroxide solution, so that's why the pOH of calcium hydroxide come out to be less than pOH of potassium hydroxide. Example 2 asks to calculate pOH of 2.2 molar HNO3. First, you will need to know what is the identity of HNO3. Is it an acid or is it a base? Because acid would produce proton, whereas base would produce hydroxide ions. So you need to be able to differentiate them, because if you plug in the concentration, then you will need to know whether it's going to give you pH or pOH. HNO3, this chemical formula contains hydrogen written first. It indicated this molecule is an acid. This acid is called nitric acid. When nitric acid dissolves in water, it's going to give off hydronium ions and its conjugate base, nitrate ion. According to the equation, you can see that nitric acid dissociates into hydronium ions or proton in this case. So that means if you take negative log of the hydronium ions or proton, you are going to obtain pH, not pOH. So that means in order to find out pOH, then you are going to relate that by the 14, because the problem gives us the temperature at 25 degrees Celsius. So this would be our step here. But how much hydronium ion would be produced, then that's when we are going to need to look at the identity of the acid. This acid, nitric acid, is one of the 6 strong acids. So that means this acid would dissociate completely into hydronium ions. So that means 2.2 molar of nitric acid will then convert to 2.2 molar of hydronium ions. So if I take negative log of these hydronium ions, then I will get pH equal to negative 0.34, and the pOH would then equal to 14 minus negative 0.34, which is come out equal to 14.34. And again, as you see from the previous lecture, we see that the pH and pOH are inversely related. So that means if you're looking at this strong acid, nitric acid with a high concentration, you can see that the pH value will come out a very small value, less than 7, but pOH have to come out as a very high value. So that way these two can add up equal to 14 at 25 degrees Celsius. Example 3, the problem asks to find out the molar concentration of hydroxide ion and at 25 degrees Celsius, and also giving us the pH of 2.45. You need to understand that pH is not related directly to hydroxide ions. Instead, pH is related to the hydronium ions or proton concentration. So we will not be able to use the pH value directly to calculate the OH. Instead, we need to relate pH to pOH, because the pOH is equal to negative log of hydroxide ions. So that means if you look at the formula above, you can see that if you know pOH, then you can find out the concentration of hydroxide ions by doing the anti-log, which is equal to 10 raised to negative pOH. To solve for this, then you will need to solve for the pOH first, which equal to 14 minus pH, and you will get pOH of 11.55. Let's check your answer real quick. The pH value tells us that it's at 2.45, which means that this solution is acidic solution. So that's why the pOH have to come out greater than 7. That makes sense. Next, to calculate for the concentration of hydroxide ions, we are going to use 10 to negative pOH, which is going to be 10 to negative 11.55. The concentration of hydroxide ion would come out equal to 2.8 times 10 to negative 12 molar. Again, going from the pOH to concentration, you are going to use the decimal place and convert that to sig fig. So we have 2 decimal places, then now it's going to become 2 sig fig. Vice versa, if you are going from the concentration to pH or pOH, the number of decimal places will then become the number of significant figures then will become the number of decimal places. So this would be your final answer. Recall autoionization of water. For pure water, the concentration of hydroxide ions is 10 to negative 7. And the concentration of proton is 10 to negative 7 as well. So as you see, this is an acidic solution because of the pH is below 7. So that's why the concentration of hydroxide ions should come out a lot lower than 10 to negative 7. So that's how you check your answer. Example 4 asks to calculate pH of strontium hydroxide. If you look at strontium hydroxide chemical formula, you can see that strontium hydroxide would dissociate into 2 hydroxide ions. So that means if you take negative log of 0.25, you are not getting pH. Instead, you are going to get POH. So that means you need to first find out POH. Then you can convert that into pH. Because strontium hydroxide is a strong base, so that means 0.25 molar of strontium hydroxide would produce 2 times of hydroxide ions, which equal to 0.50 molar of hydroxide ions. So that means if I take negative log of this, I would then get the POH. Which equal to 0.30. And to get pH, then you're going to subtract 0.3 from 14. The reason why I can use 14 because, again, the temperature of this condition is at 25 degrees Celsius. The pH would then equal to 13.70. Now let's check if this makes sense. Because strontium hydroxide is a base, the pH of a base have to be greater than 7, and the pH that we calculated is also greater than 7. So this is the correct answer. Please practice more of this concept by doing Newton Online Homework, Chapter 14.6. Thank you for watching.